Okay, so well, so let me recall what we did in the previous lecture. So we saw that given tau in the upper half plane, okay, you are able to get a biholomorphic map, namely a holomorphic isomorphism of the punctured torus defined by tau. So it is a torus minus a point, and this point is actually the image of the lattice defined by tau under the natural map from the complex plane to the torus, which is a quotient map, okay. And so this is the punctured torus, the torus defined by tau minus a point, and this is biholomorphic to the so called affine algebraic elliptic curve associated to tau, which I had called as E sub tau 2, and this E sub tau 2 was the zero set of the polynomial f2 tau xy inside C2, C cross C, Cartesian product of C with itself, and where f2 tau of x comma y was simply 4 x cube minus g2 tau into x minus g3 tau minus y squared, and in fact this biholomorphic map was gotten by in fact sending so phi2 sent the point z. I am putting square bracket z to be the element in the torus which corresponds to z in the complex plane under the quotient map. So this is the equivalence class of z, okay, and that is being sent, and of course since I am in the punctured torus, z is not a lattice point, okay, and I am just sending this to the point to the pair of complex numbers given by phi tau of z comma phi prime tau of z, and the image lands inside the zero set of this polynomial because of the first order degree 3 first order degree 2 differential equation satisfied by the phe-function, okay, and we in fact we also proved that this E2 tau is actually naturally a Riemann surface structure because it is by the implicit function theorem, it is locally a graph, and the coordinate projections will serve as complex coordinates. They will give you charts, and that these charts agree, and the fact that you can apply the implicit function theorem came from the fact that this polynomial is nonsingular, namely there is no common solution to there is no common solution to the system consisting of this equation being 0 and also the first partials with respect to x and y also being 0 simultaneously, okay. So there is no point on this locus, there is no point on this elliptic algebraic affine curve at which both partial derivatives of this polynomial with respect to first partials with respect to x and y both vanish at that point, okay. That was a non-singularity condition that was required to apply the implicit function theorem, okay, and the implicit function theorem told you that locally this locus is a graph of a holomorphic function, and therefore it acquires a structure of a Riemann surface, and then we check that all these local Riemann surface structures glue together, that is they agree, okay. In other words, the projections onto the two coordinates here actually give charts which are compatible whenever they intersect, okay. So now what I am going to do today is I am going to tell you how to extend this map to the full torus, on this side, and on the other side I'm going to extend it from this affine elliptic algebraic curve to the so called projective elliptic algebraic curve associated tau, and you see, and how that is obtained is, you see, by adding x0 as a 1 point compactification to this punctured torus, we get the torus, and similarly there also you are just going to add one extra point, the so called point at infinity as it is called in algebraic geometry, to get the projective algebraic curve. But then after you add it, it no longer lives in C2, it lives in projective space, it lives in projective 2 space. So I will have to explain what this projective 2 space is. Okay, so I will begin by trying to explain what this projective space is. So so this is just so projective space P to C. So this is so this projective space is just, by definition, P to C is just the set of lines through the origin in C3. Okay, so you look at C3, which is 3-dimensional complex space, and you look at the lines through the origin, okay, and the set of lines is called the projective space, it's called the projective 2 space. So by definition a point of P2C is a line through the origin in C3. Okay, now let us try to understand what that means. You see, if you give me C3 and if you give me a line through the origin in C3, then you know this line can be written as L sub lambda mu nu, where the lambda mu nu are the so called you may call direction ratios of the line. So you know general equation of the line would be something like you know, you would normally write in coordinate geometry, you will write it as x by lambda is equal to y by mu is equal to z by nu. I mean, this is how one would write it, the equation of line passing through the origin with direction ratios lambda mu nu, and of course the only problem in writing like this is one of the lambdas or mu's, or one of the lambda mu nu could be 0, so it is not legitimate to put that in the denominator. A better way of writing it is you can also write it parametrically as x equal to lambda t, y equal to mu t, z equal to nu t, where t is a complex number. Okay, you can write it in this parametric form, and now you see that you also see, so now what you do is given a line like this, you send it to so this corresponds to a point in P2C. Okay, and then you notice that L sub lambda mu nu is also equal to L sub lambda t mu t nu t. Okay, and of course you know mind you, I want really a line through the origin, so all lambda mu and nu cannot vanish at the same time. Okay, so I want at least one of them to be non-zero, only then I will get really a line through the origin, and of course if lambda mu and nu are all simultaneously 0, I will simply get the origin, I will not get a line. Okay, and you see if t is a complex number, you see that the line joining the origin to this point is the same as a line origin joining the origin to this point, and therefore you see that therefore you see that if you define this equivalence between triples in this way, then the quotient will naturally be the set of lines. Okay, so in other words what you do is that you have C3 minus the origin. Okay, so I am simply writing a single 0 for the point with all 3 coordinates 0, and what you do is you have this projection pi into the quotient, which is C3 minus the origin modulo an equivalence relation. And what is the equivalence relation? The equivalence relation is, well, the equivalence relation is lambda 1 mu 1 nu 1 is equivalent to lambda 2 mu 2 nu2 if and only if there exists a complex number t such that t not equal to 0 such that these three are just multiples of this by t, that is lambda 2 is equal to t lambda 1, mu 2 is equal to t mu 1, mu 2 is equal to t times mu 1. Okay. So if you go modulo this equivalence relation, what you get here is actually going to be it can be identified with P2C, the set of lines. So in other words, if you give me a point lambda mu nu here, it goes to the line L sub lambda mu nu, which is thought of as a point here, alright, and of course L sub lambda mu nu and L sub t lambda t mu t nu will be the same, they are one and the same line. Okay, so they give the same point here. So in this way we are able to think of projective 2 space as a quotient of this open set, which is the punctured 3 space, okay, by this equivalence relation, and of course we would like to do topology and geometry on it. So what we would do is, the first natural thing that we would do is we would try to put the quotient topology on P2C so that pi becomes a continuous map. So we will do that, put the quotient topology on P2C so that pi becomes continuous, and this is a very nice quotient. In fact, I just want to tell you that this quotient map is actually an open map. That's because you see, if you take a subset S in the punctured 3 space, the 3 space minus origin, and then you if you project it down by pi and then you take the inverse image, okay, what you will get is precisely the set of all lines through the origin which pass through some point of S. Okay, this is exactly set of lines through 0 passing through some point of S. This is what you will get, and in particular, you know, if S is an open set already, then the set of lines through the origin passing through points of S will give you a kind of cone generated by S, okay, and that will also be an open set. Okay, so it's very clear that S open will imply that pi inverse of pi of S is open, but then this will tell you that pi of S is open, because a set in the quotient, namely in the projective space, is said to be open in the quotient topology if and only if its inverse image is open. Okay, so the moral of the story is that this will tell you that pi is an open map, and since it's an open map, what we can immediately conclude is that since C3 is both Hausdorff and second countable, so the subspace is also Hausdorff and second countable, and since this is an open map, the quotient is also Hausdorff and second countable. Okay, so thus P2C is also Hausdorff and second countable. Okay, so basically it's Hausdorff because if you give me 2 points here, I can find if these 2 points are distinct, I can find 2 distinct points above in the lines that correspond to these 2 points below, and since that is Hausdorff, I can separate them by disjoint open neighborhoods, and then if I take the images below, I will get disjoint open neighborhoods below. Okay, and then as for second countability, I just choose a countable base here and then take its image, I will get a countable base because pi is of course a surjective open map. Of course pi is surjective because this is a quotient. okay, it is just a set of equivalence classes. So it's a Hausdorff second countable space, okay. Then the other thing that one has to notice is that this is actually in fact compact as a topological space, okay. You see, if you take in C3 minus the origin, you take the so called unit sphere, okay, which is S2C, okay. This is precisely the set of all those points with the property that mod lambda squared plus mod mu squared plus mod nu squared is equal to 1. This is the set of all points on the unit sphere, okay, and of course you know this is a closed and bounded set, so it's a compact set, okay, and it lives here, okay, and so in fact I should put sub of this, okay, it lives here, and then you know if actually from C3 minus 0 if you take the projection pi to P2, you will actually see that if you restrict the projection pi restricted to S2C, this is also going to be surjective. Therefore it's very clear that this is a continuous map, you take a continuous map and restrict it to a subspace, this is also continuous, it is surjective, this is compact, therefore that is compact, okay. So what this will tell you is that P2, the projective space, is compact since S2 is, okay. So this is a compact, so we have got a compact Hausdorff second countable space, okay. Then I need to introduce you to the so called homogeneous coordinates on P2. So let me just explain it. So you see you have C3 minus 0, and you know if you take a point lambda mu nu, it goes to, well, under the map pi it goes to a point of P2C, and the point the point that it goes to is actually the line passing through lambda mu nu, and as we have seen this line lambda mu passing through lambda mu nu and the origin in C3 actually depends only on the multiples of these three numbers lambda mu and nu, on a common multiple of these numbers, okay, by the equivalence. So what we do is we simply denote this as, we want to think of it as a point, and we denote it by these coordinates called the homogeneous coordinates, okay. So you put a colon lambda colon mu colon nu just to say that it's the ratios that matter, okay. So and it's the ratios that matter, and then once you choose to write it like this, then these three are called the homogeneous coordinates, okay. And mind you that if I multiply each homogeneous coordinate by the same non-zero complex number t, then I still get the same point, okay. So this is also equal to t lambda t mu t nu for all t non-zero complex number, okay. So these are the so called homogeneous coordinates. So let me write that down. Okay. So now what I am going to now do is, you see, I am going to show how you can turn projective 2 space into what is called a complex 2-dimensional manifold, okay. So let me recall, yeah, what was a Riemann surface? The Riemann surface was basically a complex 1-dimensional manifold. By that it's a Hausdorff second countable topological space, if you want connected, such that there are complex coordinate charts. They are all charts into the complex plane, okay. They will give you single variable coordinates at each point, a neighborhood of each point, and these charts should be compatible so that they give an atlas, and then the Riemann surface structure is defined. And in fact you normally take the Riemann surface structure to be the one that is defined by a maximal atlas, but that is just a technicality, alright. But now what you can do is, whatever we did there for one variable, you could also do it for two complex variables, and in this case, so it means that you are trying to take a topological space which is Hausdorff second countable, and for each point you are trying to get hold of an open set which looks like an open set in C2 now. That means it's homeomorphic to an open set in C2, and then you transport the complex structure on C2 to this on that open set of C2 to this open set, and then you again check that all these two variable complex coordinate charts they all agreed with one another wherever they intersect, and this is what gives rise to what is called a two-dimensional complex manifold. So what I am going to now try to tell you is that P2C is a two-dimensional compact complex manifold. Okay, so in this case there are essentially three charts. Okay, so and we say that these charts are given by on the open sets where the first variable, the first homogeneous coordinate, the second homogeneous coordinate, and the third homogeneous coordinate respectively do not vanish. Okay, so what we will do is we will set u0 to be the set of all lambda mu nu such that lambda is not 0, the first coordinate homogeneous coordinate is not 0. So you must understand that this is well defined, because if you have the first variable non-zero, okay, then any multiple then this point remains the same if I multiply throughout by a non-zero complex number, and for that non-zero complex number also, I mean for that representation also, the first variable continues to be non-zero. Okay, so similarly we define u1 to be the second homogeneous coordinate non-vanishing, and we define u2 to be the third homogeneous coordinate not vanishing. Okay, now what I want to tell you is that I am going to explain how u0, u1, u2 are actually homeomorphic to a copy of C2 itself. Okay, so for example, let me define phe0 from u0 to C2 by, well, if I take a point in u0, it's of the form lambda mu nu, lambda is to mu is to nu, these are the homogeneous coordinates, and you see the point is it's in u0, so lambda is not 0, so I can multiply throughout by 1 by lambda and I will get 1, so this point is the same as 1 colon mu by lambda colon nu by lambda. Okay, and well, I send it simply, I have to give you an ordered pair of complex numbers, I simply send it to mu by lambda nu by lambda. Okay, so this is my map, and you can check very clearly that phe0 inverse exists, and phe0 inverse simply takes beta comma gamma to it will take beta comma gamma to 1 beta gamma to the point with homogeneous coordinates 1 beta gamma. Okay, so if lambda was 1 and this was beta and gamma, I will simply get beta gamma. So you see phe0 is a bijective map. Now it's very easy to check that phe0 is a homeomorphism. Okay, so how does one check that? So one does the following thing. Well, you see you have C3 minus the origin, the punctured 3 space, and then you have the projection pi onto this projects onto the projective space. Okay, and then here you have the open set u0. Mind you, u0 is an open set because its inverse image above is all those points which are contained in the punctured affine space, and there the coordinate there it's actually a legitimate coordinate, and a coordinate vanishing is the locus of a coordinate vanishing is of course a closed set. Its complement where the coordinate does not vanish is an open set. So the inverse image of u0, pi inverse u0, is actually an open set. This is an open set, and pi restricted to that will carry it on to u0. This is also open in the projective space. Okay, and now you see I can define a map from so let us say yes. So you see what I do is from C2 I define a map by sending I will simply send beta comma gamma to 1 comma beta comma gamma, okay, which is a point here. This point actually lies here, okay, and it goes down to this map. So if I so this map actually goes down to a map like this, okay, and the fact is that this map actually lands in pi inverse of u naught, and if I compose, this map actually lands in u naught, okay. So the map is just beta comma gamma going to 1 colon beta comma gamma, which is just the image of this, okay. And of course this is a continuous map, this is of course a continuous map, because I'm just using the coordinates to give this map. So in fact it's a holomorphic map. See, a map in several variables, in several complex variables is said to be holomorphic if it is continuous and it's in each variable separately a holomorphic function, okay. So you see this is individually there are 3 variables, and the first variable is the constant, the second variable it's beta and gamma, which are anyway holomorphic because they are coordinates. So this is a holomorphic map, it's continuous, and this is of course continuous, therefore this is continuous. But what is this? This is just phi naught inverse. So this tells you that phi naught inverse is continuous, okay, and so phi naught inverse is continuous, and you will also see that phi naught itself is continuous. So I have u naught to C2 which sends lambda mu nu to mu by lambda nu by lambda, okay. So what I have above is pi inverse of u naught, and then I have this map, and this map is just, so pi inverse u naught sits inside C3 minus the origin, which in turn sits inside C3, and then this map from C3 to C2 is just, so you know, if I take lambda mu nu above which goes to this under the map pi, okay, then what I do is I simply take lambda mu nu as a triple in C3 and simply send lambda mu nu to so I'll have to divide by lambda, so I'll just send it to mu by lambda nu by lambda, and this is of course, you see, this is since lambda is not 0, okay, division by lambda is not a problem, and then this is therefore a continuous map, okay. So it's actually 3 I have 3 coordinates and I am dividing by a coordinate which is not 0, and that continues to be continuous. So this is, so you see, therefore the moral of the story is that so this should tell you this is continuous, and so and this diagram commutes. So so this was our find phi naught. So phi naught is also continuous. So phi naught is also continuous. Yeah, in fact, to be more clear, I start with an open set here. I take its, if I take the inverse image here, it's the same as taking the inverse image here and projecting it down. But if I take the inverse image here, I will first take the inverse image here, which is going to be open, but it will lie here, and then if I project it down, since pi is an open map, I'll get an open set here. That's how the inverse image under phi naught of an open set here is an open set here, and therefore by the topological definition of what a continuous map is, phi naught is a continuous map. Okay, so the upshot of the story is that phi naught is a homeomorphism. So what you do is you use phi naught, you use u naught comma phi naught as a complex coordinate chart, but now it's in 2 variables because you have identified it with C2. So there are 2 complex variables. So transport the complex structure on C2 to u naught via phi naught. Okay, so what does this mean? This is exactly the philosophy is the same as we defined a Riemann surface. So basically what do you mean by saying transport the complex structure on C2 to U0 via phe0? It means that you will we are trying to do complex analysis on U0 which is homeomorphic via phe0 to C2, okay, and so what you do is that every point in U0 will get two complex coordinates because its image here has two complex coordinates, and then if you give me a function here, a function here is said to be holomorphic at a point. If a function is defined at a point, it is said to be holomorphic. If you take the inverse of this map and then follow it by that function, you get a function from C2, and then you know how to decide when a function defined on C2 or an open subset of C2 is holomorphic, okay, and it is holomorphic if it is continuous, and it is holomorphic in each variable, okay. Therefore you can make sense of what a holomorphic function means on U0, okay. So let me write that down. So so if I write this as phi, okay, phi from C, phi holomorphic at let me say p0 in U0 if and only if I apply phe0 inverse of phe0 of p, so if and only if phe0 inverse composed with phi is holomorphic at phe0 of p0 in C, okay. So this is a natural way in which you look at this composition, okay. This is a homeomorphism and this is a function, so the composition is a function, the composite function is just apply phe0 inverse, then apply your given function, and then to decide that the given function is holomorphic at a point, it is enough to check that by definition this composition should be holomorphic at the image of that point, okay. So this is how you can give a so called complex structure on U0. So you can talk about holomorphic functions on U0, and in particular, and so you can talk about holomorphic functions from U0 into any other space which has such a complex structure, okay. Now the point is therefore we get so in the same way we get three coordinate three coordinate charts in two complex variables each, in two complex variables. So this is one is U0 comma phe0, the second one will be U1 comma phe1, and the third will be U2 comma phe2, okay. So in exactly the way I have defined phe0, I can also define phe1 on U1 and phe2 on U2 in a very natural way, and in fact how do I define it, so for example where phe1 is defined from U1 to C by if you give me a point of U1, it's of the form lambda, any point in the projective space is a homogeneous coordinate like this, it has homogeneous coordinates like this, and U1 is a place where mu doesn't vanish, so I can divide by mu and I'll simply send it to lambda by mu comma nu by mu. So this is what phe1 is, and similarly how do you define phe2? Phe2 will be from U2 to C, it will be the homeomorphism which is given by sending lambda mu nu to now it's U2, so nu is not 0, so I can divide throughout by nu, and I'll simply get lambda by nu mu by nu, okay. So we get three coordinate charts, and now notice that P2 is actually the union of all these three open sets. It's U0 union U1 union U2, because you give me any point on P2, it has if you write it in homogeneous coordinates as lambda colon mu colon nu, then you know that all lambda mu nu cannot be 0, so at least one is not 0. That means that point is going to lie in either U0 or U1 or U2. It will lie in U0 if the first homogeneous coordinate is not 0, and in U1 and U2 respectively if the second and third coordinate homogeneous coordinates are not 0. So P2 is covered by these three open sets, each of which looks like C2, and on each of these there is a chart, and now what I am going to tell you is that on the intersections these charts they are compatible, okay. So so in particular if you have a function which is defined on u0 intersection u1, deciding whether it is holomorphic using the chart phe0 or using the chart phe1 will not create any problems, okay. So this is the compatibility that allows you to define when a function is holomorphic in a neighborhood which is contained in the intersection of these two open sets, okay. So what I am going to do is now just try to explain how that compatibility comes. So these three charts are compatible. Why are they compatible? So for example, let me look at phi, the chart u0 comma phe0 and u0 comma phe0 and u1 comma phe1 and show how they are compatible. So if I take u0 intersection u1, okay, then this is contained in u0, okay, and u0 to phe0 is your homeomorphism, which is a chart into C2, and what it does is that it sends the map, it sends the point with homogeneous coordinates lambda mu nu in u0, so it's in u0, so lambda is not 0, so I am simply going to send it to mu by lambda nu by lambda, okay. On the other hand, so I am going to get a homeomorphism of this with phi naught of u0 intersection u1, okay, which if you want I will call this as v01, okay. And on the other hand, u0 intersection u1 is also sitting inside u1 as an open set, okay, and you have from here the map phi sub 1 which goes into C2, okay. And how does it go? I simply send so lambda mu nu, if it is also in u1 then mu is not 0, so I can divide by mu, and I am simply going to send it to well, I divide by mu, I get lambda by mu nu by mu, okay. This is what I am going to send it to, okay. So and therefore I am going to get this this map, so you see this is contained inside this, and here I have phi1 of u0 intersection u1, which I will call as v10, which is contained inside this diagram commutes, okay. So the transition function is simply, so the transition function is well, so if I start with beta comma gamma, I will first go to 1 comma beta comma gamma, and that will further go to under this I will have to divide by beta, so it will go to 1 by beta comma gamma by beta, okay. And you must understand that since notice that beta is not 0 because this is supposed to be in u1 as well, okay, it is supposed to be here, so beta is not 0, so then the transition function is just beta comma gamma going to 1 by beta comma gamma by beta, and that is a holomorphic function because in the first variable is 1 by beta and beta is not 0, therefore it is holomorphic. In the second variable it is a ratio of two coordinates, okay. So essentially this transition function is holomorphic, it is obviously continuous and it is holomorphic in each variable, therefore it is holomorphic, okay. So so this tells you that the charts on u0 and u1 are compatible, okay. Now you can do this with any other pair of charts and check that they are all compatible, okay. And therefore the moral of the story is that you get a Riemann surface, I mean you get a complex manifold, so called complex surface structure on the projective space. So so before I continue, let me say something, let me write it in some in the homogeneous coordinates, in using the notation of homogeneous coordinates. So what I am doing is, so here you see this will correspond to what this will go to or what this will come from uniquely will be just y by x, z by x, okay, and what this will go to will be I will divide by y, so I will get x by y, z by y. So essentially we say that the transition functions are just given by one set of ratios of the homogeneous coordinates going to some other set of ratios of homogeneous coordinates, okay, the ratio taken by the same homogeneous coordinate, and that is why the transition functions are holomorphic, okay. So P2C gets the atlas formed by these three charts and becomes what is called a compact complex two-dimensional manifold, and a two-dimensional manifold is always called a surface, okay. So a P2C projected to space becomes a compact complex surface. So in this regard, let me make a small clarification. So you see, when we talk about Riemann surface, the Riemann surface is basically a surface over the reals, okay, but if you think of it as a complex manifold, it is complex one dimensional, okay. So as a complex manifold, it is like a curve, okay, it is one dimensional, and so a Riemann surface, the word surface in as an adjective in Riemann surface is with respect to the reals, okay, and here you have a complex, when you have a complex two-dimensional manifold, it is called a surface over the complex numbers, okay, but of course if you think of it as a real manifold, then it will be four-dimensional, okay. So so that is it, we have P2C becomes a compact complex two-dimensional manifold. Now what I have to do next is so the moral of the story is that I can do complex analysis on P2C, because on any open subset of P2C I have charts that tell me clearly whether a given function is holomorphic or not, and so I can do my complex analysis on this. Now I told you that the purpose of this whole discussion was to tell you that this affine elliptic algebraic curve associated to tau can be compactified by adding a single point, and the compactification will live in the projective space. So in fact, for that what I will have to do is that I will have to basically look at projective space, and I will have to tell you when a polynomial in 3 variables, if you can take the 0 locus of that in projective space, that naturally becomes a Riemann surface.